We spend our days swiping across glass screens, gripping steering wheels, and holding coffee cups. The physical world we built is incredibly smooth, but the equipment we use to navigate this polished environment wasn't designed for it at all. The very tips of our fingers are covered in biological hardware built for a wildly different landscape. If you zoom in closely, the skin on your fingertips stops looking flat. It reveals itself as a rugged terrain of massive canyons and valleys. Millions of years ago, our ancestors lived high up in the forest canopy. To survive, they needed a way to grab onto rough bark and slippery branches without falling. These deep ridges acted like natural treads on a tire, creating intense friction. You can see this exact same gripping technology actively at work when you look at other primates, like chimpanzees and gorillas, navigating the wild today. It's such an effective biological solution that nature actually engineered it twice. Koalas, despite being marsupials with completely different genetic lineages, developed almost identical friction ridges to hold onto eucalyptus trees. So if we left the trees behind long ago, why do we still carry these jungle suction cups in a world of concrete and glass? Because that exact same friction is what allows humans to manipulate fine tools, build tiny microchips, and hold a smartphone with precision. Without those ancient grooves, everything we touch today would slip right through our fingers. Gripping an object is only half the job. These ridges also operate as an incredibly sensitive, high-definition data array. When you drag your finger across silk or a coin, the ridges vibrate against the microscopic bumps. Those vibrations travel down to Pacinian corpuscles beneath the surface. These cells amplify the sound waves, translating them into a detailed map of what you touch. This sensory array is so advanced that it even has a weather mode. When your fingers get wrinkled in the bath, they aren't soaking up water. Your nervous system is actively shrinking your blood vessels to create deeper valleys in the surface of the skin, giving you better traction in wet conditions. This dual capacity for both brute friction and microscopic perception allows the fingertip to resolve textures that the rest of our skin simply misses. The engineering behind this interface happens long before we take a breath. When a fetus grows in the womb, it is surrounded by amniotic fluid. Around the 10th week, the middle basal layer grows faster than surrounding tissue, buckling into deep folds. As the baby moves, chaotic currents of amniotic fluid push against the soft skin, permanently sculpting precise loops and whorls by week 17. Because these currents are incredibly chaotic and impossible to replicate, the resulting patterns are completely unique to that specific moment in time. Even a genetically identical clone wouldn't end up with the same lines. We see this reality with identical twins. They share the exact same DNA to build their bodies, yet their fingerprints are entirely different. And because this pattern is anchored all the way down in the stem cells of the basal layer, it functions as a permanent, self-repairing master blueprint. If you accidentally scratch your finger, the skin simply regrows using that same exact master file, keeping your identity completely intact. Beyond sensing the environment, these ridges also actively interact with it. Tiny glands in the skin constantly excrete a protective oil called sebum to keep the tissue flexible and waterproof. This continuous flow of oil coats your fingertips, turning them into natural biological stamps. Every time you touch a glass or a metal handle, you leave behind an invisible, oily map of your unique ridges. Long before modern forensics, ancient humans recognized that these marks were distinct to each person, and they put them to work as the world's first identity security system. Thousands of years ago, in places like ancient Babylon, potters and government officials would press their thumbs directly into wet clay tablets. They understood that this biological impression was an absolute guarantee of authorship. It was a physical promise that they stood behind their work, a signature that could never be forged. Today, we've swapped out the wet clay for high-tech scanning glass, transforming our biological signatures into the primary authentication for our bank accounts and private data. Modern biometric scanners isolate the geometry of ridge endings and splits, called minutiae, converting your handprint into mathematical code. Technology is going deeper. Engineers are developing vascular scanners that look through the skin to map the blood vessels pumping beneath those ridges. By combining the surface topology with the living biology underneath, it creates a multi-layered profile that verifies your presence with near absolute certainty. The patterns on your hand remain a permanent tool for interaction. They are the evolutionary equipment that connects your physical body to the tools, the history, and the digital networks you rely on every day.